Hello and welcome to our lesson on differentials. So differentials are basically components of slope, and to make it make sense I'm going to connect to some things we've already discussed. So let's start with just slope in general. If we're given a function, let's say y equals f of x, we know that the slope of that function, or the average rate of change, is describing the change in the y values with respect to the change in the x values over a closed interval. So we have a formula for slope that we tend to think about as y2 minus y1 over x2 minus x1. But again, the y2 minus y1 represents the change in the y values, and the x2 minus x1 represents the change in the x values if we're looking at some closed interval for a function. And again, that's the slope, or the average rate of change. So we can start by saying, again, what's familiar is that slope represents the change in y values with respect to the change in x values. Okay, so that's like when you first learn slope, that's what you learn. And then we talked a whole bunch about derivatives, and we know that when we are looking for a derivative, and when we find a derivative of a function, we call it f prime of x and many other things, but what we're doing when we find that derivative is we are approximating the instantaneous slope, or the instantaneous rate of change at a specific point. So we're taking the closed interval and we're making the distance between the two x values get infinitely small to find that instantaneous rate of change at a point. So when we find a derivative, we say that our slope, or our dy dx, is used to approximate the change in y with respect to x. So again, we say that our derivative of y with respect to x is approximating the slope, instantaneous slope, which we just said is the change in y with respect to x, and this happens as the change in x approaches 0. So as the distance between the x values in our closed interval becomes infinitely small and approaches 0, then we are approximating the instantaneous rate of change at that single point that the interval converges to. Okay. Then so far, everything we've talked about in terms of dy dx, our derivative, has been a single concept. So the dy dx has been a single concept. So the derivative of y with respect to x, again, a single concept. However, it's going to be convenient for us at times to separate the meanings of the two pieces. So the dy and the dx are going to be looked at separately in this lesson. And so those dy and dx components of slope, right, those are what we call differentials. So specifically, we say dy is the differential of y, and we say dx is the differential of x. Okay, now if we were to look a little more closely at it, what you should be connecting these things to, that differential of y is the change in our y values with respect to the differential of x, which is the change in our x values, approximately. Okay, so we're going to separate those two things. Specifically, what we're going to be trying to do is find the differential of y. Now, not always, but typically that's what we're doing. We're finding the differential of the output. So one more step here. If we were looking at, I don't have enough colors, the derivative of y with respect to x being called our f prime of x, our derivative, and now I want to separate these components. Again, if I want to be able to solve for that dy dx, well, dy dx is being divided by, dy is being divided by dx. So if I simply multiply that over, I will have a generic formula to find dy. So this means that dy all by itself would be f prime of x multiplied by dx. So again, we're separating those two components of slope, and you'll see why when we get to some examples why that's a helpful thing to be able to do. Okay, so the differential of y, again we're calling that dy, is always going to be the product of the derivative and the differential of x. So it's going to be the derivative multiplied by the differential of x. Again, we're calling that dx. And we can do two things. We can, just like when we're finding derivatives in general, we can find a generic equation, a formula for our derivative, for our slope at a point, and then we can actually evaluate it at a specific point. It's a similar concept here. We can calculate a generic formula for the differential of y. In fact, we just did that. We said dy would be equal to f prime of x dx. And then if I knew values for x and dx, then I can also evaluate, get a numeric value for that differential of y. So we can either calculate a generic formula or we can calculate a numeric value if we are given information about x and the change in x. Okay? So let's look at an example, try to wrap our brain around the concept a little bit. Let's say we're given y is equal to 2x cubed minus 5x. I could ask you to just find the differential of y, which would be a generic equation we're going to be looking for. I could then say find the differential of y when we're looking at a specific value of x and a specific change in x, and then we're going to be looking for a value, and then hopefully we'll be able to interpret what we're doing. So let's do it. Let's find the differential of y. This means we are looking for dy. That's the question. Okay, so if I just found dy dx, that's my traditional derivative. I know how to differentiate this thing with respect to x. The derivative of 2x cubed is going to be 6x squared, and the derivative for negative 5x would just be a negative 5. Well, now it's just an extra component here. Instead of looking for the derivative of y with respect to x, I just want the dy component, so just the differential of y. So again, I'm going to multiply over that dx and say dy is equal to the quantity 6x squared minus 5 multiplied by dx. And so this is a generic formula for that differential of y. Okay, now this generic formula is going to give me any change in y values if I know a specific x where I'm looking and the change in x values that I'm looking at. Okay, and again, we're going to put some numbers to this and hopefully it'll make sense. So here, in the second box, we're going to find the differential of y when x is equal to negative 2, and dx, which is the change in x, is equal to 0.1. So I have a formula, right? dy is going to equal 6x squared minus 5 times dx. I'm just going to be inputting the two values I'm given into that formula. So I have 6 times, instead of x squared, negative 2 squared, minus 5, and that quantity is multiplied by dx, the change in x, which is given to us, or differential of x is given to us as 0.1. And then we can go to the calculator or try to math this out. Let's see, negative 2 squared is 4, 4 times 6 is 24, 24 minus 5 would be 19, times 0.1 should be 1.9. Although, I just, don't exactly trust myself all the time, so let's just confirm with the calculator my insecurities. And oh yeah, I know how to math. Okay, so we get a differential of y equal to 1.9. So again, here's a generic formula, generic equation that we can calculate for our differential of y. And then if I know specific values for x and dx, then I can actually calculate a value for my differential of y. Now, what does that mean? Let's try to... Sorry, my OCD issues are setting in. Let's try to explain in this last box here. So when we are looking at x equals negative 2, and then a change in x of 0.1, the change in y is 1.9. So that means if I went from an x value of negative 2, just 0.1 of a unit over, so I went over from negative 2 to negative 1.9, that as I do that along this particular function, the y value should be increasing by 1.9 units. So this is telling me to start at x equals negative 2, end at x equals negative 2 plus the change in x, which was 0.1, so that would be negative 1.9, and then if I start at x equals negative 2 and I end at x equals negative 1.9, when I make that particular change in my x values, the corresponding change in y values is 1.9. So dy is, why did I write that like that? What in the world? Okay, so dy equals 1.9. So just to put it in words now, let's try to put some math there. What I would say is, if I started at x equals -2, or as x increases from -2 by 0.1 of a unit to -1.9, the change in y is 1.9, or y increases by 1.9 units. So as x increases by 0.1 of a unit, let's just say 0.1 units, just to make this a little more concise. Oops, come on, pen. From the starting value of -2 to -1.9, y increases 1.9 units. Okay, so you're told the x value where you're starting, you're told to change this much, which means you can find the x value where you're ending, and over that interval, the differential of y tells us how much the y is increasing or decreasing if it was negative. Okay, so hopefully this makes a little bit of sense, and I think these problems are a little more practical when we start putting some applications in, but let's do a few more without the words before we complicate. Alright, for example, find the differential of y for the given values of x and dx. So we're going to calculate a formula first and then input the given values to actually calculate the differential of y, an actual value for it. So in this first one, I'm going to rewrite the square root of 3x plus 2 as 3x plus 2 to the 1/2 power. Now let's find the derivative of y with respect to x to introduce our differentials. So using my power rule, I have 1/2 times 3x plus 2 to the -1/2 power, and then my chain rule times the derivative of the inner function is going to be 3. And so if I clean this up a little bit, dy dx is going to equal, let's see, it's going to be a 3 on the top of the fraction, and then it's going to be 2 times the square root of 3x plus 2 on the bottom of the fraction. So that's just my derivative. Now if I want to know just the differential of y, I'm going to solve for that by multiplying over the dx. So when I multiply this side by dx, and again multiply this side by dx to get dy all by itself, then dy is going to equal, that dx I can leave out to the side there, or I can move it to the top of my fraction, which might be a little bit easier. So now I have 2 times the square root of 3x plus 2 as my equation. Okay, so that's the equation. Now I can use this equation to actually find a value, knowing that x equals 4. I'm going to plug x equals 4 in, and knowing that the change in x, which is a synonym there for the differential of x, that's the change in the x, and let me go back up here. Remember, the differential of x represents that change in x values. So those are two ways to give you the same information. If that differential of x is 0.15, that's going to get plugged in there. So now we're going to say, with another color, that dy is going to be equal to 3 times the differential of x, or the change in x is 0.15 there, and then we divide by 2 times the square root of 3 times x, which is 4, and then a plus 2. So we're looking at, let's see, 3 times 0.15, and the numerator is going to be 0.45 in the numerator. 3 times 4 is 12, 12 plus 2 is 14, so I have 2 radical 14 in the denominator, and we may as well just approximate this, which is what you're going to be asked to do when you get to your homework assignment. So maybe we go straight to the calculator from this step and avoid the possibility of making an error there. So 3 times 0.15 in the numerator divided by 2 and radical 14 in the denominator. Oh, let me just type in the original. Again, this is my insecurity here, but just in case I made a silly mistake. Okay, so we're looking at a change in y of approximately 0.0601. I mean, I could keep going. That's probably going to be good enough. I'd say running to the, I don't know, thousands, 10,000s place. It kind of just depends on how your decimal looks. Like, if there were a bunch of zeros, we probably want to keep, 3 or 4 significant digits in there. But this looks good to me. So that is our differential of y for this particular problem. Now again, just to sort of wrap your brain around what we just did. We said for this particular function, if we started at x equals 4, and then we went 0.15 units away, which would be going to 4.15, that as we move from x equals 4 to x equals 4.15, the y value is going to increase by about 0.0601 units, so not much at all. Okay. Now I think this would be a good place for you to pause the video and try this out if you are feeling confident. If not, let's go ahead and work through this one together. Again, I want to find my differential of y, so let's differentiate. Let's find dy dx. In this case, it's going to require our quotient rule, so let's call this f and call the bottom g. I need f prime g minus fg prime divided by g squared. So we have the derivative of the top, which is just 2, multiplied by the bottom, which is just x plus 1, minus the top, 2x minus 5, times the derivative of the bottom, which is just 1, and that's all going to be divided by the bottom squared. And again, we're going to clean this up a little bit. We're going to do some evaluating, so you technically don't have to. I just want to, I suppose. So this is 2x plus 2 here, and then we're going to be multiplying by 1. It's not going to change the 2x minus 5, but distribute the negative, so negative 2x and then plus 5. So we're going to see those x's cancel, and we're going to be left with 7 over x plus 1 squared. Now again, I want to solve for my differential of y, so I'm going to multiply both sides by dx. So dy is going to equal 7 times dx divided by x plus 1 squared. Okay, so there's the formula to calculate the differential of y at any particular value of x and given any change in x. Now let's plug in the stuff we know. So I know x equals 2, that's going to go in there. And I know the differential of x, the change in x, is going to be negative 0.03, that's going to go there. So our specific dy in this case is going to be 7 times negative 0.03 divided by 2 plus 1 cubed. And 2 plus 1 is 3, 3 cubed is 27. Nothing's going to reduce. Actually, the 3's can kind of reduce, but I'm not going to mess with it. I'm just going to put that in the calculator. So 7 times negative 0.03 in the numerator. Come on, fat fingers. 2 plus 1, which I know is 3, but again, I'm just going to type it in there in the denominator. So let me change this. This is going to be approximately negative 0.00, and then let's just go 78. Okay. Now it doesn't specify where to round, so again, I'm going to just go with this is a good enough answer. And I'll box in the whole thing so I get my dy in there. But that's the concept. And so in this particular function, what we're saying is if we went from x equals 2, and then we went negative 0.03 units away, so we went to 1.97. So if we went from x equals 2 to x equals 1.97, that as we moved left like that, the y value would be decreasing. The outputs would be decreasing by negative 0.0078 units. So we know the change in y with respect to the change in x at that particular x value. Okay? So hopefully we're making sense. Let me just separate those. Okay, now let's look at a couple of word problems so we can see how this actually applies to some useful situations, some practical situations. In economics, we use differentials to find changes in things like revenues and costs and profits. So the change in revenues or profits or costs, and we do this in lots of ways. We've done this already. We found changes in these things, but we can find them now with respect to changes in the independent variable. So if I just find the change in my revenue knowing a specific change in my x values, right? I can use differentials to calculate that. So we call this marginal analysis. It still goes with derivatives and the things we've been doing before with revenues, profits, and costs, finding their derivatives. It's just now separating the components, okay? So again, this is called marginal analysis. And actually, differentials are useful for marginal analysis. They're useful for estimating error or possible error when that might enter when like measuring physical quantities. Like if you're measuring the side of a rectangle and your ruler isn't so accurate, then you can estimate the error that might happen in finding the area of the rectangle, knowing the error that you've created in the measuring the side length. Okay, so something like that. We can also use this to approximate radicals. There are actually lots of applications of this. We're just going to focus on a few. So let's look at number 4. We're going to use differentials to approximate the change in cost corresponding to an increase in sales of 1 unit. So we're given a cost function. We are looking at x equals 10. So at that particular place, if our sales increase by 1 unit, that means the change in the x's is 1 unit. So we know the change in the x values, we know the x value we're looking at. That should be enough information for us to use differentials to find the change in the cost that corresponds with that change. So when it says here to find use differentials to approximate the change in the cost, that means to find the differential of the cost. So let's find dc in this case. It would be like dy. Okay, so that's going to be our question. So again, we're going to take our derivative. Let's go green. So if I found the derivative of c with respect to x using my power rule, 2 times, let's see, 0.025, why? It's going to be 0.05, but I just don't know why. Okay, 0.05, so this will be 0.05 x to the first power, plus the derivative for 8x is just going to be 8, and then the derivative for our constant is going to be 0. So here's our derivative of c with respect to x. I know the change in x, I know the x value, I want to find just the differential of c, the cost. So again, I want to solve this by multiplying dx over. So I'll say dc is the quantity 0.05x plus 8 multiplied by dx. And now we have values we can plug in. So I can say dc is going to equal 0.05 times our x value is 10 plus 8 times our differential change in x is going to be 1. So remember this dx, change in x, same concept. And here our x equals 10, getting plugged in there. And let's make these correspond. Okay, so then let's see, 0.5 times 10, 0.05 times 10 plus 8 is going to be 8.5. Let's see, multiply by 10. Yeah, that's going to move the decimal ones. Add 8, and then multiply by 1. So yeah, 8.5. And so since this is 8.5, and this is the cost, it doesn't give us units, but I'm going to assume that this is in dollars. So let's say 8.5 here and assume that the change in cost is $8.50. Let's be more specific. So again, back to what this means. If for this particular company, if they can increase their sales by just 1 unit, so if they increase sales from 10 units, that's where we're starting in this one, to 11 units, that by increasing the sales from 10 units by 1 unit to 11 units, their cost will go up $8.50. So I don't have enough colors. By increasing sales from 10 to 11 units, costs increase by $8.50, and again, I'm just going to assume dollars here. It's my bad for not putting well, $8.5, $8.50. My bad for not putting the units into the problem, but we'll just assume dollars. Okay. All right, so hopefully we're doing okay. Next one, similar concept here. It says a retailer has determined that the monthly sales X of a radio are 200 units when the price is $40, but they decrease to 160 units when the price is $50. Assume that the demand is a linear function of the price. Find the revenue as a function of X and approximate the change in revenue for a 1 unit increase in sales when X equals 175. Whew, okay, that is a lot to unpack there. If I can kind of rewind from the end here, we're trying to find the revenue. Remember, that's all of the money that you're bringing in. That's how much does each item that you're selling or manufacturing cost times how many are you actually selling or manufacturing. So X times P is our equation for revenue. Well, we have X obviously, but we don't have P, and that's where the beginning information comes in. So up front here, they have determined, this retailer, that 200 units are sold when the price is $40. Because it says this is a linear function, the demand function, the price function that I'm trying to write, I'm going to write that as a coordinate. So 200 units corresponds with $40. So that's an X and that's a price. And then it says that when they decrease to 160 units, the price is $50. So we have 160 units corresponding with a $50 price. And so I can find my slope here between my 2 points. My change in y values, or in this case p values, would be 50 minus 40. My change in x values would be 160 minus 200. So we end up with 10 over a negative 40, and that's going to be a negative 1/4. And a negative should make sense because we're decreasing. Okay, so as we move from from 200 to 160, the price. As the price goes up, the price is going up, but the x's are decreasing from 200 to 160. Okay, so we got our negative slope. And then we have a formula that says y, in this case p, minus y1 is going to equal x times x minus x1, or m times x minus x1. So we're going to have p minus, I'm going to use p1 here as 40. And you can use the second coordinate, it doesn't really matter. Slope is negative 1/4. That's going to be multiplied by x minus x1, which will be 200. And I'm going to run out of space. Use my lasso tool. I know you wish you had that. Hey, maybe you do if you're taking notes with your iPad. Just want a little more space. Okay, so p minus 40 equal to, if I distribute, that's negative 1/4 x, and then positive 200 divided by 4 is going to be 50. And then I just need to add the 40 over. So p is going to equal negative 1/4 x plus 90. So there's our demand function. So this is demand function. Demand function is p, lowercase p, price function, demand function, same thing. Okay, so there's our demand function. Now remember, revenue is what we were trying to work on here. It says find the revenue as a function of x. So for revenue as a function of x, let's go with revenue equal to x times p. So in this case, r is going to equal x times negative 1/4 x plus 90, which means r is going to equal negative 1/4 x squared plus 90x. Okay, got the revenue. And now finally, the question. Assume that the demand is linear, so you find the revenue, approximate the change in revenue. So find the change in revenue. That's dr. For a 1 unit increase in sales. So a 1 unit increase, that means the change in x is 1, or dx is 1, and then pretty explicitly given here that x equals 175. Okay, again, I'm going to lasso this over. That's the given information. Now let's find our Oopsie. Let's find our derivative. I don't have enough colors. How about this orangey looking color? Okay, so let's differentiate r. We're going to say dr dx, the derivative of r with respect to x. Negative 1/4 times 2 would be negative 2/4, which will be a negative 1/2. And x to the first, plus the derivative for 90x is just going to be 90. And then to solve for dr, we know we're going to multiply dx over. So negative 1/2 x plus 90 multiplied by dx is our formula. And now we're going to evaluate that formula at the change of x of 1 and x value of 175. So dr, maybe I need another color. Purple. Looks good. So we'll say dr is negative 1/2 times our x value is 175 plus 90 times dx, change in x, 1. And now we know dr, when we go to the calculator, half of 175 plus 90 is going to be what, like 250? Don't don't try to hurt yourself like I'm trying to do here. Oh, yep, I was right. I'm like 3 for 3. Okay, so 250 there. And again, we'll say $2.50. So, when this company, that was a lot of work to get to that answer. The actual new part of what we did, not so hard, but the pre-work of finding the demand function, not so fun there. What this means is when this retailer increases sales from 175 units to 176 units, their revenue increases by $2.50. Okay, so let's try to state this somewhere. When sales increase from 175 to 176 units, revenue increases by $2.50. And that would be technically the best way to answer that question. But if you just said dr equals 250, technically you're not wrong, because you found the differential of r. Okay, let's look at another example. Next one. Suppose the profit derived from selling x units of an item is modeled by p equals 0.0002x cubed plus 10x. Use the differential dp to approximate the change and percent change in profit when the production level changes from 50 to 51 units. So we know we're trying to find dp. We know that we're going to go from 50 to 51 units, so the change in x, or dx differential of x, is going to be 1. And oh, yep, it's like, where's the other information? Well, if we are starting at x equals 50 and then going to 51, that's telling us two things. It's telling us the starting x, so this is our starting x value, and it's telling us that we're going from 50 to 51, so our change in x is 1 unit. Okay, so it's not as explicit as it was in the previous problem, but we have everything we need here. We have a function, we are looking for the differential of p, we have the differential of x and x, so we should be able to differentiate and make our calculation. So let's go with dp dx. Let's take the derivative of p with respect to x. We multiply 0.0002 by 3, which gives us 0.0006. Subtract 1 from the exponent, so it becomes an x squared. And then the derivative for 10x is just going to be 10. So dp, which sounds good right now, a little caffeine, is going to be the quantity that we just got multiplied by dx. Alright, now we're going to plug in. So we're going to say dp is going to be 0.0006 times our x value of 50 is going to be squared plus 10, and then we got to multiply by 1. So in this particular case, Calculator says, I'm not even going to try, 6 multiplied by 50 squared, add 10, and then times by 1, not necessary, so we get 11.5, and these are profits, so we'll say $11.50. So when they produce 50 units and then increase to 51 units, the profits are increasing by $11.50. So that is the approximate change in our profits. Now, it asks us to do one additional thing. It asks us to find the percent change in profit when the production level changes here. What is the percent change in profit? So if you want to find the percent, like when you're trying to find the percent, for a quiz that you took, you take the number of problems that you got or the points that you got and you divide by how many points there were total, right? So it's a similar concept here. If I know that my differential of profits, my change in profits is 1150. If I knew the total profits at 50, I could find the percent change. So my percent change, let's get another color here. My percent change is going to be that little portion that we just found, that little change in profits, divided by the total profits at 50. Okay, so in this particular case, DP we just found was 1150. Not centered. It's going to bother me. 1150 here. The total profits at 50 I can find by evaluating my actual profit function at 50. So I can find my profits at 50. So this little change divided by what happened total should give me that percent change. So I have 0.0002 times 50 cubed plus 10 times 50, and just going to go out on a limb and say that that's going to be an approximation. So I already have 1150 in there. Let's just keep that on the bottom, 0.0002 times 50 to the third power plus 10 times 50. Yeah, we get 0.0219-ish. Okay, so as a percent, this is be about a 2.19% increase. And that is our percent change. Now, I don't know if I'm going to ask you to do the percent change in the homework, but if you're actually this business, it's helpful to see that number. If I, am trying, if I'm an analyst for a company and I'm trying to explain to them that the change in profit is $11.50 when they're going from 50 to 51 units, they're like, okay, they see the concrete number, but how does that compare to what the total profits were in the first place? So then seeing it as a percent puts it into perspective, if that makes sense. So calculating a percent change is a useful thing. Again, percents are helpful for perspective, okay? But in your homework, I think I'll just stick to finding that piece, so hopefully you'll be okay with that. All right, we got one last one where we are going to switch gears just a smidge. So all the three that we just looked at, those are all marginal analysis. We're finding how profits, revenues, costs are changing with respect to a specific change in X. Now we're going to use our differentials to calculate or estimate an error. So for example, and these are very simple, they sound kind of bad. So the radius of a ball bearing is measured at 0.7 inches. You're told that the measurement of the radius is correct to within 0.01 of an inch. Use differentials to approximate the possible error in computing the volume of the ball bearing. So we've got a radius of a ball bearing being 0.7 inches. I'm going to write that down, 0.7 inches for a radius. And you're told that it's correct within 0.01 of an inch. What does that 0.01 of an inch represent? That's the change, right? The change in the possible measurement. So this 0.01 of an inch is the dx, or the possible change in x. Not x, r in this case. All right, that radius is correct to within 0.01 of an inch. And we're going to use differentials to approximate the error in computing the volume. So the volume of the ball bearing, which in this case is a sphere. So we are trying to figure out dV. Possible error, the possible when it says possible error, recognize it's the possible change. So if you just calculated or measured your radius at 0.7 inches, obviously you plug that into your volume formula and it spits out a volume. But if there is a possible change, like it could possibly be off by 0.01 of an inch, then obviously your volume could have some error in it as well. So the error in the measurement extends to every calculation that would follow using that measurement. So we want to find the differential in the volume, the possible error or change in the volume. So our volume formula for, in this case, a ball bearing, which would be a sphere, volume for a sphere is 4/3 times pi times radius cubed. So let's take the derivative of that volume with respect to the radius, because that's what we have the change in, that's what we're given. So if we do this with respect to the radius, then this is just normal power rule. 4/3 times 3 is going to be 4, so we're going to have 4 pi r squared for our derivative, and then we multiply over that dr. So dv is going to be 4 pi r squared times dr. Now we've got everything we need. We're going to plug the 0.7 in right here. We're going to plug the 0.1 in right here, and that's going to calculate exactly what we're asked to find here. So now we'll say dv is 4 pi times our radius of 0.7. Oopsie, I missed a little detail. Maybe you were seeing what it is already, and I could put it in the end here, but I don't want to confuse anyone at the end. So let me back up right here. This, if we're off within 0.01, or it's within 0.01 of an inch, that means it could be 0.01 of an inch greater than the actual measurement, or it could be 0.01 of an inch less than the actual measurement. So really, this should be, that was a giant eraser, should be plus or minus 0.01 of an inch. No, I erased the wrong one. This one. Let's make not a giant eraser. This one. Our change in our radius could be greater or less than the 0.7 by 0.1 of an inch. So plus or minus 0.01 inches here. So now when we go to plug that in, we're going to plug in the plus or minus. It doesn't affect the calculations. We just want that to be in the final answer because the volume could be bigger than we projected, or it could be smaller than we projected. So we're still going to put 0.7 in. Oops, now I'm red. Back to pink. Sorry. 0.7 in here, and that's going to be squared. And then we're going to multiply by dr, which would be plus or minus 0.01. And so we're not going to type the plus or minus when we go into the calculator with this. It's just going to be in our final answer. So it's one big product of, let's see, 4 pi and 0.7 squared and 0.01. And so this is going to be approximately plus or minus 0.06158, I don't know, wherever you want to stop with the decimals if it doesn't specify. The more you keep, the more accurate it is. So the potential error in our volume, the volume could be 0.06158 cubic inches more than what it is if we use 0.7 as our radius, or it could be that much less than what we actually calculate. And volume would be cubic units, so we'll say cubic inches. So the possible error in the volume is we're going to be greater or less than expected by 0.06158 cubic inches. Okay? Now again, this could be used to do some cool stuff with actually, when I was in college, I had to do this. I had to approximate radicals. We weren't allowed to use calculators to approximate like the square root of 146 or something. Like I know it's close to 12, but differentials actually could be super useful for that process. If it's something that you want to look up, it might be worth your time. But calculators are great for that too. So hopefully you have enough here to get going on your assignment. I know it's a lot to take in, but you're just separating components that we've already been finding. It's like an extra step to things we've already done. So hopefully manageable, but as always, if you need some extra help, then just reach out. Alright, till next time, take care.